Good morning, everyone present here. I sincerely would like to thank Priyanka ma'am for inviting me to present, deliver a talk on machine learning algorithms for data science. Uh, and for as you know that the topic that I have been assigned is machine learning algorithms for data science. So I would like to start with what is data science. So the simplest data science meaning would be, applying some scientific skills on top of data so that we can make this data talk to us, right? And what we exactly mean by applying scientific skills on top of data is that is that the data science is an umbrella term which encompasses multiple skills and scientific techniques. So what are these techniques that are that data science comprises of? Are the data visualization, data manipulation, statistical analysis, and machine learning. So I think so far we are only talking about the basics. So then when we combine all these scientific skills into one, what we get is nothing but data science, right? I hope I'm audible to all of you.
Yes, ma'am. You are audible.
Okay.
Thank
So
you.
the first, thank you. So the first skill here that data science comprises of is data visualization, which is an essential component of a data scientist skill set. So in simple terms, data visualization is an amalgamation of science and design in a very meaningful way. Next is the data manipulation. Normally, the raw data which we get from different sources is extremely untidy, and drawing inferences from this untidy data becomes very difficult. So this is where the manipulation comes into picture. It is a technique which helps us to refine this raw data and make it more organized so that finding insights from this raw data becomes very easy. So that's about it. Very brief. I'm talking about very brief about all these terms. They are one of the subjects in their own when you actually go dive deep into data science. So further, then we have statistical analysis, which helps us understand data through mathematics, of course, and in that a lot of mathematical equations are involved which help us understanding the nature of the data set, and also in exploring the various relations between the underlying entities that we would like to draw inferences from. And finally we have the buzz term machine learning, which is a subfield of artificial intelligence, where we teach a machine how to learn on the basis of input data. So, this is where we build scientific models for the purpose of prediction and classification. So, next we talk about the relation between artificial intelligence, data science, and machine learning and deep learning. So here, as you can see in the picture, in the Venn diagram, um, it shows this Venn diagram gives us a little bit of hint to what the relation between these fields are. So the humans, that we learn from our past experiences, and machines execute the instructions given by the humans. For example, if I show you pictures of cats and dogs, you'll be able to see the difference between a cat and a dog and identify accordingly. In a similar fashion, when the machines are trained to learn from past examples, they will be able to make predictions just the way humans can do. So in short, machine learning is a study of algorithms and methods that learn from examples and experiences. But in current times, artificial intelligence is the buzzword. So it is a bigger concept to create intelligent machines and that can mimic human abilities such as thinking and behavior. So it is like it encompasses the machine learning algorithm. So I will use AI for artificial intelligence henceforth. So AI enables machines so intelligent that they can have a genuine human to machine interaction and can perform human tasks. So you can say that AI is essentially embedding intelligence in machines that it can learn, understand, and use the knowledge learned to carry out in one or more tasks. So it is basically, for example, building a robot is will be a task of artificial intelligence. Whereas machine learning is a subset of AI that trains machines how to learn from data without being programmed explicitly. So let me tell you the idea behind it. In this, we take a machine learning algorithm, give it some data specific to the problem or domain for which you want to train the machine. Let's say cat versus dog classification, then that machine learning algorithm can automatically learn the underlying relationships and patterns within the data in such a way that it can make a prediction for unseen data. So, more technically, machine learning is all about learning a mapping function that learns the mapping between the input variables to output variables through training data. So here, then you have deep learning, which is again a subset of machine learning as seen here, which is a technique to perform machine learning inspired by our brains through the network of neurons. Okay. And data science. So data science is actually it involves the concepts of mathematics as well as artificial intelligence and machine learning. So, so I think it's very clear from the diagram. So machine learning is everywhere these days. I am sure you'll all agree to this. The origin of the concept of machine learning dates back to 1980s, but it is only in the past 5 to 10 years that machine learning has actually gained so much momentum. There are two reasons behind this sudden popularity of machine learning. First is the data. Today's world is full of data, be it pictures, videos, texts, etc. And the data is not going to slow down any further in the future. Apart from this, the computational abilities of computers to handle this data has also increased in recent years. So, with data as the backbone, machine learning provides the key to unlock meaningful hidden insight from the data. So, we see machine learning all around us today. It has become such an integral part of our lives that we use these applications without even realizing that machine learning is behind all these things, isn't it? So machine real world applications are many. To name a few, I have jotted it down in the form of a diagram. So machine translation. Apart from this, you have converting a text from one language to another language automatically. Things like spam detection in Gmail, tagging objects and people in photos, recommending books, movies, products, while doing online shopping. And the biggest and simplest example of a machine learning application is the Google search. So when we search for something on Google, Google shows up the most relevant web pages related to that search. So I think all of us have already experienced all these things. So how actually machine learning is a highly interdisciplinary field which builds upon ideas from cognitive science, computer science, statistics, optimization, among many other disciplines of mathematics and science. So, how important is the role of mathematics in understanding machine learning? So, well, I think it is important, all of you will agree, but just to draw an analogy here, I would like to quote an example of learning to drive a car. So when you I heard this, even this is not my example, I heard it in a very good talk given by I don't remember the professor's name, but it was in NPTEL lectures. So I would just like to quote his example here. He said that when you actually drive a car, even when you're learning, you can drive a car even without knowing the mechanics behind it. But if the car breaks down somewhere and we are unable to fix it, and neither are we able to reach a mechanic, then we are stuck, right? So, similarly, one can use machine learning easily for various applications without a strong understanding of mathematics behind it. However, if the mathematical foundation is strong, then it will be an extra edge to fix the problems arising while applying a machine learning algorithms on different problems. So, to summarize, I would say that the more mathematics you know, the wider perspective you will have, and the faster you will be able to grasp machine learning algorithm. So, then we come to the types of machine learning. Um, so the first type is supervised, then unsupervised, and then we have something called as the reinforcement learning. Supervised learning is the most popular paradigm for the machine learning. It is the easiest to understand and simplest to implement. I think all of you will agree to this. So it is very similar to teaching a child with the use of flashcards. Given data in the form of examples with labels, we can feed a learning algorithm these example label pairs one by one, allowing the algorithm to predict the label for each example and giving it feedback as to whether it predicted the right answer or not. So the algorithm of the relation between examples and their labels. So I'm talking about the supervised, where we have provided the machine with the labels, given the algorithm, and over time the machine will learn with the examples and labels. So when fully trained, supervised learning algorithm will be able to observe a new, never before seen example and predict a good label for it. So supervised learning is often described as task oriented because of this. It is highly focused on a single task, feeding more and more examples to the algorithm until it can accurately perform on that task. So this is the learning type that you will most likely encounter, as it is exhibited in many of the following common applications, which I just mentioned in the last slide as well. Then comes your unsupervised learning. So unsupervised learning is very much the opposite of supervised learning. It features no labels. Instead, the algorithm would be fed a lot of data and given the tools to understand the properties of this data. So from there, it can learn to group, cluster, or to organize this data in a way such that a human can come in and make sense of the newly organized data. So, what makes unsupervised learning an interesting area is that an overwhelming majority of data in this world is unlabeled, right? So, having an intelligent algorithms that can take our unlabeled data, huge unlabeled data, and make sense out of it is a huge source of potential profit for many industries. That alone could help boost productivity in a number of fields. To give you examples, for example, I think in my talk, I will be restricting myself to supervised learning more precisely to support vector machine. But I would just briefly would like to talk about unsupervised and reinforcement learning to just give you an idea of what they are. So, for example, if we had a large database of every research paper ever published, and we had an unsupervised learning algorithm that knew how to group these in such a way so that you were always aware of the current progression within a particular domain of research. So now you begin to start a research project yourself and looking at your work into this network that the algorithm can see. As you write your work up and take notes, the algorithm makes suggestions to you about related works, works you may wish to cite, and works that may even help you push that domain of research forward. I think all of us have experienced that when we search other research articles on elsewhere or Springer or anywhere, it shows the recommendations based on our search. With such a tool, your productivity can be extremely boosted. So this is an example of unsupervised learning. So because it is based, unsupervised learning is based upon the data and its properties, we can say that unsupervised learning is data driven. So, so few examples are, as I said, recommended systems, buying habits, grouping, user logs, etc. Then finally, we have reinforcement learning. It is fairly different when compared to supervised and unsupervised, where we can easily see the relation between supervised and unsupervised. So the relation to reinforcement learning is a bit murkier. Some people try to tie reinforcement learning closer to the two by describing it as a type of learning that relies on a time dependent sequence of labels. However, it is in a general, it is simply, it makes a little bit more confusing. So, I would like to describe reinforcement learning as learning from mistakes, as how the child learns from its mistake. So, place a reinforcement learning algorithm into any environment and it will make a lot of mistakes in the beginning, just like the child, just like a small child. So long as we provide some sort of signal to the algorithm that associates good behaviors with a positive signal. So many a times when we tell our child that if you do this, I mean, if you do not repeat this mistake, we will give you a chocolate. And for the bad behaviors with a negative one. So if you similar, very, I think all of you can draw an analogy to bringing up a child in this. So we can reinforce our algorithm to prefer good behaviors over bad ones. So over time, our learning algorithm learns to make less mistakes than it used to. Just like a child, when he or she grows, grows up, he or she is more, much more comfortable in making decisions so as to what is good or what is bad for him or her. So usually the reinforcement learning scenario is used to play uh, games. I mean, to develop video games and resource management. So it is good for navigating complex environments. For example, Google's data centers. So they used reinforcement learning to balance the need to satisfy our power requirements, but do it as efficiently as possible, cutting major costs. So this is one example of reinforcement learning. So not all classification predictive models support multi. So let's see. I think next we will talk more about supervised learning. In these, there are two algorithms: regression algorithms and support vector machines. So um, So in my talk, I will be restricting myself to support vector machines. Regression algorithm, actually support vector machine is a kind of extension of logistic regression. Regression algorithms, I have given some example here. What will be the temperature tomorrow? How much discount can you give on a particular item? So these are all examples where the logistic and support vector machines, of course, we will talk more in detail from the next slide. So, not all the classification prediction algorithms models support multi-class classification. So, algorithms such as logistic regression and the support vector machines were basically designed for binary changes. Means only classifying two things at a time into two different categories. So first we will define what is classification. So given a collection of records, a training set, each record or each entry in the data, each record contains a set of attributes. One of the attributes is the class label, and then we have to find a model. Model is what is the mathematical function for the class attribute as a function of the values for other attributes. Okay, so here the objective is that previously unseen records, if we apart from the training set, if we are giving a new entry, new record to the machine, it should be assigned a class as accurately as possible. That's what our model should do. So this is about the definition of classification. So for example, here we have the height and weight. Um, so if we want to classify the height and weight of a person, then we have certain training examples for many training examples for our model, and we have the linear classifier for separating, for classifying the height and weight and um, of of a person, and um, and then we can, if we give new height or weight, then the model is able to classify it. So this is a gist of how the model looks like. We will see how we have to develop this and what are all these things. What are all these W, X, and B representing in just after a few minutes. So I'll come to this again in a minute. So before that, I want to talk about SVM versus deep learning. So I think nowadays deep learning is everywhere. Everybody is talking about it, um, and it is more into research also, deep learning. But I would like to quote here by this is a graph taken from a research paper by Cervantes. It shows that the authors who used only deep learning algorithm versus the SVM algorithms, their accuracy was comparable. As you can see, sometimes it was more also, like here in this case, using SVM, they have got a better accuracy than the deep learning algorithm. And on the other hand, when the combination of deep learning algorithm and support vector machine was used, the accuracy was increased, as seen from the blue graph. So, so what were these algorithms? You can find the all the references in this research paper if you would like to go further in this field. So, in support vector machines are still a very good classification supervised learning approach to classify any given problem. So I think I'm audible to everybody.
Yes, ma'am, you are audible. Please continue.
Yeah, yeah. Okay. So in machine learning, as I said, that classification is a supervised learning approach. It's used to analyze a given data set and to build a model that separates data into a desired and distinct number of classes, like how we saw here. There are many good classification techniques in the literature, which include K nearest neighbor, Bayesian, artificial neural nets, decision trees, and support vector machine. So from all these techniques, support vector machine is one of the best known techniques to optimize the expected solution. It was introduced by Wapnick as a kernel-based machine learning model for classification as well as regression tasks. So the extraordinary generalization capability of the SVM, along with its optimal solution and its discriminative power, has attracted the attention of data mining, pattern recognition, and machine learning communities in the last years. So that's what this paper also says. So I think now we will start with formalizing the problem and seeing how, now that we have represented our points visually, so we will, the next job will be to separate these points using a line or a hyperplane. Let's see how to do that. So it's a very sophisticated idea, very simple implementation. So here you have a space where you have some negative examples and some positive examples. How do you separate the positive and positive samples from the negative samples? So what Wapnick suggested was that if we separate these samples by drawing a straight line, uh, like this, so by drawing a straight line. So but the next question would arise, that which straight line? But which straight lines? So maybe this or this. So there are many. Okay, so maybe what we do is draw a line like this with a view to putting a widest street that separates the positive and from samples from the negative samples. So this approach is called widest street approach. So first we will define the decision boundaries, then we will see how to put the constraints on this decision boundary such that it is widest. We follow the widest street approach, and then we see the kernel functions. So to put a straight line in such a way as the separation between the positive and negative samples is as wide as possible, um, first of all, we want to think about how we would make a decision rule that would use that decision boundary. So let us take a vector. Let us imagine that we have got a vector uh, say W, constrained to be perpendicular to the median. So this is the median, and this is the vector which is perpendicular to the median, to the line of the street, median line of the street. Then we also have some unknown, say U here, U vector. So what we are really interested here is that whether or not this unknown is on the right hand side of the street or at the left hand side, whether this unknown is here or here. Okay. So we want to project that vector U down on the one that is perpendicular to the median street. Why we would like to do that? Because we will have the distance in this direction, or a number that is proportional in this direction. So let me use a pointer here. So this is the direction. So we want to project this vector down here because we will have the distance in this direction. Okay, and further out we go, the closer we will get to be on the right hand side of the street. So we can take that W, dot it with the U, unknown U, and measure whether or not that number is equal to or greater than some constant C. That's what I just mentioned in words, that we would like to project this U on this vector W, because then it will go, because this is in this direction towards the street, perpendicular to the median of the street. And when we take the dot product, we actually measure whether or not that number is equal to or greater than some constant. Okay, so the dot product is taking the projection on W, taking the projection of U on W, and bigger that projection is, the further out along this line the projection will lie, and eventually the projection will be so big that it crosses the median line of the street, and we will say that it must be a positive sample. This is an idea. So without loss of generality, we say that the dot product W dot U plus B is greater than equal to 0. Then the sample is positive. Which sample? The U, the unknown sample U. So, but here, so this is our decision rule. Okay, so we have arrived at our decision rule. This is the decision rule. So here, there are two troubles. We do not know what constant B to use, and neither we know which W to use either, isn't it? So still the problem is yet to be formulated. So, but we know that W has to be perpendicular to the median line of the street. So, but there are lots of W's that are perpendicular to the median, because it could be of any length. Yet we have not specified anything about the length. We just know that W has to be perpendicular to the median line. So we don't have enough constraint here to fix a particular B or a particular W. So what we are going to do next is that we are going to lay some additional constraints so that we can actually calculate a B and a W. Okay, so next task is to lay constraints such that we are able to get the values of W and B. So next we are going to take the dot product of W with a positive sample X plus, and we add B. So we are going to want this to be greater than equal to 1. So here in the previous one, U was unknown. This time we have taken a positive sample here, dotted it with view, and added with B, and we are saying that it is greater than equal to 1. So in other words, a sample can be an unknown anywhere in the street and be just a little bit greater or a little bit less than 0. But if the sample is positive, we are going to insist that this decision rule gives a value of 1. That's what we have done here. Okay. Likewise, we have a negative sample. Then we are going to say that W dot X minus plus B is less than equal to minus 1. That is, this decision rule is going to give us a negative 1 in case that U is a negative sample. That's what we have done it here. So there is a separation of distance here of -1 to +1 for all the samples. But again, we have not made our lives easier. We have introduced 2 more equations. So a pair of these equations are very difficult to solve. So what we are going to introduce is a new variable y sub I. This is just a mathematical convenience. So we are going to introduce this y sub I, whose value is 1 for positive samples and -1 for negative samples. So for each sample, we are going to have a value for this new quantity y. Okay, and the value of y is going to be determined by whether it's a positive or a negative sample. So positive samples, it's going to be +1 for this, according to this equation, and -1 for this situation. So multiplying these two with y sub I, that means we have to multiply. When we are multiplying y sub I with this, it will be positive y sub I, and when we are multiplying y sub I with this, it will be multiplying negative, because the value is negative for negative samples. So when we do that, we get only one equation. How? Because when we are multiplying minus y sub I here, the inequality turns, and the negative cancels out, and you are left with the same equation as the first one. So we get this equation for xi in the street, in the margin. I think in general terms, this thing is called the margin or the gutter. So we have added the additional constraint and say that it's going to be exactly 0 for all xi's inside this street or margin. Okay. So we have got an additional constraint. So the value of this sample, the value is exactly equal to 0, but the values of this or this is not equal to 0. Value of this is also exactly equal to 0, because they are exactly in the street, but not 0 for these samples because they are outside. So now I think we have got some expression that talk about some constraints, and we are trying to figure out how to arrange for the lines to be such in the street that such that it's separating the positive and negative samples as wide as possible. So maybe better figure out now how we can express the distance between these two, isn't it? Now the next objective here is to find out the distance. So we have got a vector here uh, to x minus to a negative sample, and a vector here to the positive sample x plus. So what's the width of this street? So the width, we take the difference of these two vectors, x plus minus x minus. So if I only had a unit normal, that's normal to this median, so this is the median, take the median. So if we take the normal to the median, and we had the unit normal, that's normal to the median line of the street. If it is a unit normal, then I can just take the dot product of that unit normal, normal with this difference vector, isn't it? And this will give me the width of the street, unit normal of this street, of the median. Unit normal will come out of the street, it will be out of the screen, okay? And when it is dotted with this difference vector, which is towards this direction, it will give me the width of this street. So we are talking about in a three-dimensional plane. So you can imagine how the unit normal of this median will come out of the screen, and the difference vector, which is in this direction, both dotted together will give us the width of this margin. So the width is the difference vector dot the unit vector w. So the unit vector is denoted by w divided by the norm, or the mod of w, which will give us the magnitude. So this will give us a scalar, which is the width of the street. So we have got the equation of the constraint that separates the sample and the margin. That was this. Okay. We will now make, you know, so from this equation 2, from this equation, we have x plus. So what we will do is a little bit of algebra here, and when you open the bracket and you want to find here when you, for the positive sample, you will see that the x plus bar is actually 1 minus b. W dot x plus bar is 1 minus b. Okay, so this is actually 1 minus b, and this together, like this, the value of this is 1 uh, minus 1 plus b. I hope I'm not making any mistake here. You can cross check with this equation for the positive and negative samples, and you get this value when you therefore when you substitute and simplify, you get the width of the street to be 2 upon mod w. I hope it is clear to everyone. Am I audible?
Ma'am, you are audible. Please continue. You are audible.
Oh, okay. So we have got an expression here that we want to minimize. Okay, we want to minimize this. Uh, and we want to, so again, using some of the basic algebra here, we can say that if you want to maximize this 1 upon, like if we want to maximize this, I can just remove the constant and say that I want to maximize 1 upon norm W, or minimize 1 upon 2 norm W square. I can say this, right? It is just like, if we take the minuses, exchange the minuses in both the sides, when it is in inequality, the inequality sign changes. So that's how we have it here. So it's like simple maths. So we have got some constraint that we would like to honor, and we have got the expression that we want to find the extremum of. Okay. Therefore, we will, so what next will come? We will use the Lagrange's multiplier that will give us a new expression which we can maximize or minimize without actually thinking about the constraints anywhere. Okay, it's what we are doing. We are having two expressions here. We would like to convert it into one using Lagrange's multipliers. This is the expression that we will get after we use Lagrange's multiplier. How we have got this, I will tell you in the next slides. So before that, I will talk about Lagrange's multipliers method. So actually, the Lagrange's multipliers method, it turns a constrained optimization problem into an unconstrained. So as I said that the you don't have to worry about the constraints after you have applied the multiplier method. So by setting the gradient of a function to 0. So in this figure, you can see that the function f of xy on the set G. So this is the function which is constrained on this set G. Okay, and this happens when the gradients of both f and g are proportional. Okay, if the function will have the maximum or extremum only when the gradients of both f and g are proportional. Okay, that is L is equal to del of f, that is the gradient Laplacian of the function f, minus lambda, which is the Lagrange's multiplier of the constraint, that is del g minus b. Here is the constraint here. So setting del L is equal to 0 gives us the values of x and y for which this function will have the maximum on the set G. So what we have done, we have reduced this optimization problem into one using the Lagrange's multiplier. Okay, so this is the basic of the Lagrange's multiplier method. So it's very useful because using this method will allow the entire algorithm to not get stuck in the local minima problem. Okay, unlike the other neural networks, local minima is a very big problem in the neural networks. Okay, so since we are in the convex space here, so it's applying the similar thing here in our problem 2. So this is our maximization problem. Constraint was this, and these are the Lagrange multiplier alpha i's for every I. Okay, and then we have to set the Lagrangian to 0, which implies that we have to take the partial derivative with respect to the changing quantities. So the changing quantities here are the W, that is the vector, the width of the street, and B the constant. So these two are the ones which we were actually, when we formed the decision rule, we were actually wanting to find out the values of. This is the constant and this is the vector, I mean, width of the street. Okay, so when you take the partial derivative with respect to w and with respect to b and equate it to 0, you get the values of the vector w and mm, an expression like this. So here, if you note that the alpha i's will be 0 for some samples because of the fact that when the sample is inside the margin, it's the value for this is 0, right? This was the constraint that we have put. So for some samples, the value of alpha i's will be 0, and for some it will not. So when we substitute w, the value of w, into this equation, into the Lagrangian, we get this expression. Okay. So I think it is clear so far, the differentiation part and the value that we got using this, and now we substitute it back into this expression to get this expression. And when we little bit of simplification, we get the final expression. So here we want to find out what this maximization depends on with respect to these sample vectors. So what we see here is that this is only depending upon the dot product of a pair of sample vectors. So what we found out here in this equation, that the optimization depends only on the dot product of the pairs of the samples. That's what we will have to keep in our mind. Okay. So the decision rule looks like, with the value of w put in it, like this. Okay, so the decision rule that we had in the beginning, yeah, so here in this we have put the value of w, and we get the expression this, and this will be true for any positive sample. So it is a convex space, this is very, mathematicians can prove that all this is happening in a convex space. It is, the entire algorithm will never get stuck in a local maximum. This is in the contrast of the neural networks, where there is a very big problem of local maximum. Okay, so this was about the samples which were linearly separable. Okay, this was about the samples which were linearly separable. So with all the things that we saw, so see here that the samples are linearly separable. What if the samples are not linearly separable? Something like this. Something like this. Okay, these are the samples which are not linearly separable. Then what we do is we get the points in another space. Okay, in another space where they are easily separable. So what we need is a transformation from the space that we are into where things are more convenient. So in this case, if we take these points using the transformation phi to this space, that is, this is our input space and the feature space, and the points now will be linearly separable. Okay, and in the last slide we saw that the maximization only depends upon the dot product. So we need to maximize the dot product of the transformation. So this is the best thing about mathematics, that you can directly take the concept of the dot product of the vectors and accordingly apply it to the transformation without even you have these results already proved, and you can easily apply it here. So that's how you have got the dot product of the transformations as well. So when you take these dot products, you have it in the form of a function k, which is the kernel that gives the dot product of these two vector in another space. Okay. uh, without actually knowing what this transformation is. It is like magical. So you don't even know what the transformation is, but you can still get uh, get your samples separated linearly only using the dot product kernel functions. So we have got in general a general method that's convex and guarantees to produce a global solution. We've got a mechanism that easily allows us to transform this into another space. So what we did was that we first defined the decision rule, and then we put some constraints based on the location of we use the widest street approach, and then we put some constraints with the restriction that if the sample is inside the margin, it will be exactly equal to 0. And then we formulated the optimization problem, um, and which was solved using the Lagrange's multiplier. And then we saw that the maximization only depended upon the dot product of the pair of samples. So this was about the maths behind the support vector machines. So these are the popular choices of kernels used: the homogeneous polynomial kernels, non-homogeneous polynomial kernels, radial basis function kernels. So in recent times and the research community, there is a lot of the experiment with different types of kernels involved. For example, the fractional calculus was used to modify this kernel, the radial basis function. Instead of the exponential, the Mittag-Leffler function was used as a kernel, and they were able to get very good results in the mechanical engineering field. So it was a very good experiment, and the accuracy was also better than the radial basis function, RBF kernel. I think RBF is one of the most popularly used SVM kernel. So likewise, there is a lot of research going on, a large amount of data generated and collected at each moment. So they are using the SVM to in the development as well as solving some challenging problems in order to identify um, various the right kernel and adjusting its parameters efficiently. So the trends and the challenges in SVM are: the large amounts of data are generated. The supervised and unsupervised learning methods of machine learning are the for responsible for transforming these data into useful information. So SVMs have proven to be one of the best supervised learning methods in various applications. But however, there are several challenges while using the SVM. First of all, it is in it is difficult to solve when two or more of them are presented. It means if in a multi-class problem, it is a bit of challenging. However, that also in the recent research work, if we want to apply the SVM onto a multi-class problem, that also has been done using first converting converting the multi-class into a binary one wide multi-class data set into multiple binary classification data set, and then you fit a binary classification model on each of it. So that was one of the challenges. And then you have um, the large scale problems, that is overfitting and undersampling, are some of the challenges that SVM has. And then kernel choice and parameter optimization. As I said, that the fractional calculus is coming into picture due to this only. So automatic kernel choice and calibration of the parameters in a low computational cost fashion is a problem that has not been completely solved. So the design of new kernels, the research community, the design of new kernels has shown to improve the performance of SVMs. And then you have the real-time applications of SVM. So as I showed you in the previous slide, that when SVM, when combined with deep learning, has shown much more better results, promising results. So I think it is always there in every field of science and engineering, that when the fields are combined, multidisciplinary, they tend to give good results. So real-time applications involve the text categorization, hypertext categorization. In recent research, it was shown that implementation of a text document classification framework that uses the SVM approach uh, was also successfully implemented. Then some authors, they evaluated three machine learning algorithms, k-nearest, SVM, and adaptive resonance associative map, and evaluated them for Chinese document categorization. And they found out that SVM was highly efficient in learning from all these well-organized samples of moderate size. So why this thing is important? Because SVM, as you know, is a supervised learning approach. So then image classification, it has been, SVM has shown very good results in image classification, in identification of kidney stone detection. Then um, then some authors have developed to handle device feature with low cost and high performance to enhance early detection of melanoma. So it's a common classifier that shows high accuracy for classifying all these medical conditions. So recognition of Indian signs based on a dynamic hand gesture recognition technique. So in real-time scenario, so this was also done using SVM. And then you have bioinformation. So it was semi-supervised, like many techniques combined with SVM. So they say that if they are semi-supervised SVM-based feature selection, exploits the knowledge from unlabeled and labeled data. So experimental results on the gene expression data of lung cancer, show that the semi-supervised SVM achieves a higher accuracy and requires shorter processing time compared with the well-known supervised method. So and then you have the handwritten character recognition. So I think the Wapnick himself has written 2 to 3 papers on this, which were published much later of when the method he came up with the method. So handwritten digital recognition is developed now and uses a small number of patterns for training purpose, and then recognition performance is improved by using the bag of visual words technique to construct images, feature vectors, and each visual word is described by scale invariant feature transform method, and SVM classifiers are employed here. And similarly, you have the face detection. It is used the large way to improve the detection performance. SVM here is used to improve the detection performance. So, human to detect the human face in digital video. But one of the problems of face detection is the large variations because of some factors like viewpoint, extreme eliminations, and expression changes. So this is leading to large intra-class variation, which makes the detection a little not robust enough. But it can be solved using developing the locality sensitive SVM using the kernel combination algorithms. See, why I am telling you all these things that in the era of deep learning algorithms, uh, all these applications have found solutions, good quality, good accurate solutions with the very simple SVMs. I'm not saying that the SVM was implemented this in its simplest form. Obviously, there has to be a good amount of research. You need to modify the SVM, modify the kernel, or it's like how I said, semi supervised SVM. In its modified form, SVM will perform wonders much better than deep learning techniques in some scenarios, and it is a very easy implementation because of the strong mathematical foundation that it has behind it. So likewise, there are many applications where SVMs have been applied um, very successfully to achieve greater accuracy and plan such as classification of credit card for frauds, tagging of melanoma, plant species classification, and so on. So this was about SVM. So if there are any, I think I am done. Maybe I have voted everybody with a lot of mathematics, I believe. I this is because of my background. I am a mathematician by profession. So really sorry if I have loaded you with a lot of mathematical terms. And please let me know if you have any questions and any suggestions uh, in order to improvise or no, it's after all, it's a faculty development program. So I'm open to questions and suggestions.
Thank you so much, ma'am.